All right, everyone. So I want to show you the calendar for this week right now. We are here, and tomorrow you have these 3 pre-lectures due. They're just really simple. They're on just simple regression. And this bonus survey that you might have noticed hasn't opened up yet. That's because it's March 1st is unofficial St. Patrick's Day, and we're just doing a survey that opens as soon as, I think at midnight, as soon as it turns March 1st and lasts for 24 hours, and it sort of tracks behavior during that time. You'll see when you open it why it's only open for 24 hours. So it's kind of a fun survey. We've been doing this every year, and so for a long time. The very first time unofficial happened, I was actually teaching a math class at 9 a.m., kind of like this. It was a big class in Greg Hall. It was before you could do online. It was completely full, and it was linear algebra. And it was funny because I thought, oh my goodness, this is great. The students are so excited. You know, why aren't they always this excited? You know, it was really fun. And but then a fight broke out, and I had no idea what was going on. I said, you know, I think I need a bouncer. And they said, yeah. And then I found out it was unofficial. And seriously, and then I started teaching stats, you know, huge stats class. I actually had to hire my own bouncers, real bouncers from clubs and stuff. They loved to do it. They were fun. And so, and it worked because we didn't have, you know, people, the university didn't know how to handle it very well. Now they handle it really well, and I don't teach those giant classes on the quad anymore, so I'm not faced with it right now. But I still do these surveys, so they're fun to see. I just wanted to get students, you know, see how they, you know, they're dated, like when you turn it in. So we want to see as the time goes on how people respond. That's basically the idea. So just fill it out. It's kind of fun. All right. So that said, where's the rest of the calendar? The rest of the calendar is coming up tomorrow. I'm sorry I don't have it now. But the Monday homework, it should be right here. The homework that's due Monday night is up there, and it covers what we're doing today. Chapters, all this week's stuff on correlation, simple correlation and regression. And it's pretty long. There's a lot of problems. It's pretty easy, but it's long. I just want to give you practice. So I suggest starting it early. Okay? So that's the deal here. Any questions? Okay. So let's go and finish up the chapters 23, 24, and 25. I hope I get through them all. So let's go to the document camera. And here we are on page 118. And what are we talking about here? Okay, so we're talking about correlation between 2 variables, between x and y. And remember, the deal is that we have to change them to z-scores to get this standard measuring stick before you can compute the relation, how close they are to a line. You have to get them in the same units. So we change them to z-scores, right? That's what we did last time. We changed both the x and the y to z-scores. Then once they're in z-scores, we take their products. And here's, you know, if they're above average in both, they're going to get positive z-scores. If they're below average in both, they'll get negative z-scores once we translate them to z-scores. And if these positives, you know, when negatives are associated with negatives and positives are associated with positive, we're going to get this positive correlation. Whereas when you're the opposite, when you're high in, like, below average in x, but above average in y, and vice versa, then you're going to get a negative correlation. So when we do this calculation here, all it's doing is really taking these products and seeing basically which quadrant they're in and how strong they are. How, you know, the bigger the correlation. See, we have 1 in each quadrant, but the reason we got this positive correlation of 0.5 is because these are stronger. They're further from the average here. They outweighed these. Okay? If these outweighed, then you get the negative correlation. All right, so that's the idea. So you change it to z-scores. So what does that mean in terms of doing these transformations? Adding a constant to all the x or y's is not going to change our. Basically, doing any linear transformation, changing scale isn't going to. Think about it. If the correlation between height and weight in inches and pounds is 0.6, let's say, it's not going to change just when you go to the metric system. That's unit free. So any change of scale isn't going to affect the correlation coefficient. So adding a constant does not change R. Multiplying all the x or y values, as long as you do it to all of them, by a positive constant doesn't change R. But what if you multiply it by a negative? What's that going to do? It's going to change the direction. If you multiply all the y's and keep the x's the same, it's going to change the direction. If you multiply all the y's and the x's by a negative number, then it will change it and then change it back, right? So it changes the sign, but doesn't change the strength, the absolute value of the correlation. All it does is change the sign. You can check that out for yourself. What if you interchange all the x and y's, like we call one, like the correlation between weight and height is the same as between height and weight, right? So interchanging all the y's does not, x's and y's, as long as you interchange all of them, that doesn't change R, right? And changing units doesn't change R. So it's really pretty simple here. The only, just be careful if you multiply by a negative number. Okay, so now there's this outlier problem. What is that? Remember, we're measuring the strength of a linear correlation. So sometimes you have outliers. When do you have an outlier? That's just look at all these data points here. They follow this nice line, and it looks like the correlation is very close to 1. That's without the outlier. Where's the outlier? It's this point that's an outlier. It's way off the rest of the data. And sometimes we know that's a typo, and we should just throw it out. If it's a typo, the correlation coefficient should be used with caution when there are outliers, right? Because why? Because look what would happen if we include this. Let me show you. Let's go to, I think for simple plots like this, we should just be looking at the visual, because it's much more powerful than me explaining it. I mean, the visual in action. So let's see what we should do. We should go to this data program here. I'm clicking here, and I then click on scatter plots, and we can create our own, like here, I'm just going to create a blank. Here we have a blank plot. Okay. So let's make one like that. Okay, that's really looks like it's, and here's your correlation coefficient, right? Here's your regression line. See how it's really nice and it's almost close to 1. But what happens if I add an outlier? Like let's add a point way out here. See how it changes it dramatically? Why? Because it's trying to fit a line to that. We'll look at that in a minute, but all of a sudden it became negative, right? And if I got rid of that, let's get rid of it again, delete a point, it'll go back to being very strong. Okay, so let's do this, let's start over, and let's do the other example where we have no correlation to begin with. So we have, let's add points here. So we have the other graph, plot B, looks like this. I'm just trying to get the correlation about 0. Here it's about 0, and the regression line is just a straight line. There's no correlation between, as x goes up, y doesn't go up or down. All right, so we have that, but then what happens to this? Watch what happens to this if I add an outlier. An outlier is a point really far from the data. So let's say I add this outlier way up here. See how it changes it to almost a perfect correlation? Because it's trying to fit a line through all the points. So what's the lesson here? The lesson here is that the correlation coefficient can be deceptive when you have outliers, and it's important to look at the data. Now, if these outliers happen to be just a typo and you know they're impossible, like what happens in our data set, we know somebody can't be like 10 feet tall or something, and weigh 5 pounds or whatever, some kind of crazy outlier, it's just a typo, then we should delete them. But sometimes they're real. Sometimes they're, and you shouldn't delete them because they're real data. So you have to think about them. You don't want to delete real data just because it's unusual. That's very important. to include. All right, so that's the idea. So let's go back to the document camera and write that down. All right, so here it is without the outlier, and you have a correlation of r is almost 1. And then when you include this outlier, it's going to try to fit something through, and you can get something that's almost 0, let's say. So r is approximately 0, depending on where you place that point, with the outlier. So this is with the outlier. This is your outlier. So, okay, so for which plot does it lower the correlation? So here, including the outlier lowers r, right? Lowers r. But here, you start off like this with no correlation. So without the outlier, r is about 0. Without the outlier. Here's your outlier. Now, when you include the outlier, you get this line like here. This is with the outlier. So this is with outlier. And you get r is approximately 1. So in this case, the outlier raises r. Okay? So outliers are have strong effect, but they should only be thrown out for good reasons. What would be a good reason? Like a typo. Otherwise, you should include them, but you should be aware of how the correlation coefficient is affected and report, both situations, with and without the outlier. All right, here's another example of how you have to be careful with correlations, something called ecological correlations. What are ecological correlations? They don't really have anything to do. The name is not very helpful. Ecological correlations are correlations based on averages. Okay, they're based on averages. So, and the caution is they're fine, but don't apply them to individuals. So that is, each data point represents an average over a group of individuals. And what they tend to do, they don't always, but they tend to inflate R. That is, they tend to give higher correlations than you get for individuals themselves, right? So for things like, if you look at fat in people's diet and how much breast cancer, for example, they get, you're going to see, like when you base it on countries, the average fat throughout the country and the average breast cancer rate throughout the country, you're going to see a very high correlation. But that doesn't mean that you can apply that to individuals. The correlation is much, much lower for individuals. So here's an example where this is just one that the correlation for education and income, right, is about 0.44. It's positive, but people tend to use a different statistic, this one that's, but if you take the average educational level and the average income for each state and look at the correlation between the 51 pairs, including Washington, D.C., you get this much higher correlation. So people use that because it's more dramatic. Oh yes, getting more education is going to really, there's a much higher correlation. That doesn't apply to, this one applies to individuals. And why is it? It's because within each state there's a lot of spread, but the average wipes out that scatter and just looks at between states spread. So here's a visual. So the graph on the left represents income and education for individuals in 3 states. So here's 4 individuals in state 1. Okay? And here's another 4 from state 2. And here's another one from state 3. Okay, and there's a lot of scatter here. But if I took the average state, took these 4 and averaged these 4 both on their education and on their income, I'll get 1 point. And same with the crosses, these 4. I guess we only have 3. Oh no, here's another one. Okay, so these. I'll take the average there, and then I'll take the average of the 4 people here. And do you see how so these are all averages here, and they have a much stronger correlation. So R is stronger here, okay? Why? Because it wiped out the within-state scatter, all this within-state scatter. So here there's more scatter right? Because you have both. Because you have both within group or within state and between state scatter. Because you have both within and between state scatter. So that tends to lower the correlation. Whereas here, you have less scatter. Because averaging eliminates the within less scatter, because taking averages eliminates the within group. It's true for every group. Here it states within state scatter, okay? Leaving only the between. Okay, you can say we have more points, but it's more than that. It's that these are the, it's not, more points doesn't always mean more scatter. It's that you've got a lot of scatter within each state that's eliminated here. So which one should you trust? They're both right. It's just you should apply this one to the states and this one to individuals. That's the idea. Let me show you another visual. Let me show you a visual, and then we'll, so this is the, basically this is, okay, individuals versus individuals, and this is state versus state. And the individuals, you know, okay. So this tends to inflate R. So let's just do another, let's go back to the, I'll show you what I mean. So let's go to the, here again. So, let's go to a data set right here on states, on state data, right here. And the data set includes measurements on the 51 states. Okay, this is old data, but it's a very good illustration of this. And so here's the variables, but they also then grouped the states by region. They averaged them by region. So the New England states, they took their average for each variable, etc. The, you know, far western states, the Rocky Mountain states, etc. So let's look at some of this data. So if we look at the scatter plot, and for example, let's look at, oh, there's lots of variables you can look at. Let's look at poverty in the states and teacher salary. Okay, so we have this regression line here. Excuse me. Here's the regression line, and we have this correlation. The more poverty, the lower the teacher's salaries. But now let's look at averaged over the region. So I have to choose a split, sorry. So I'll choose a split on division here. Okay, get rid of that. All right, so what do we have here? For example, what's this region? Whoops, I added a point. I did not want to add a point. Sorry, I have to delete that point. It was this one. Okay, so I just want to label the points. All right, so what's this point right here? That's the west, south, central. What's this one? East, south, central, and you can see the states here. Okay, the ones, these are very poor and they don't pay teachers very much, whereas up here, they're richer and they pay people more. So this must be New England, etc. And so look what happens when you add at the correlations. So the correlations are stronger in absolute value. Here, for the individual states, we have negative 0.25, and here it's almost double that, 0.5. So that's the idea, but it's not always the case. So you can look at this data and let's see, what is it, like maybe poverty and let's see, how much crime there is. So they're very close here. Still, the divisions are a little bit stronger. So who's this? DC, Louisiana. Okay, so that's the idea. It's fun to look at this data. Do you understand? It's not always the case. You can look through here and it's not always going to happen, but it tends to happen. So beware. The whole point is, don't make, this is fine. Just apply the correlation to what it's talking about, to these averages. Don't apply it to the individual states. You have to use this graph for that. That's all. Just know which one's which. So let's go back to the document camera and let's write down some more. So here's an example. It says, for each of 5 classes, the average percent on the midterm and the average percent on the final were calculated, all right? And the correlation for the 5 pairs was 0.97. Okay, so we have final. So we'll do this with our data as soon as you take another exam, and we can see how it might do the same thing if we average for the sections. All right, so here's the midterm, and here's the final, and they say there's this extremely strong correlation. They're probably really close to each other, right? So there's some correlation here, but they're probably really close. Okay, so there's 5 points here. Can you see them? There's 5 classes. Now let's say, does that mean that the scatter plot for all the students would be nearly a straight line? No, because look what would happen. The midterm and the final, they're spread around each one of those. So they're going to be spread out in each direction. So even though you have these averages the same, let's keep them the same, there's going to be spread everywhere around them. Within each one, there's going to be spread in both directions. So you're going to get, for all the individual students, so this could be hundreds of students, hundreds of individuals, you're going to have a lot more spread. So if R is equal to 0.97 here, R is going to be much less than 0.97 here. Does that make sense? Do you understand? Here's those, we can take those same points. That's the average. Maybe somebody scored right at the average, but those individuals are going to be really spread out within each class. Do you understand? Okay, so that's the idea here. And correlation is not causation. We know this, right, already. What? Shoe size and reading level are, never confuse these. Just because you see correlation doesn't mean one's causing the other. Shoe size and reading level are highly correlated among elementary school kids. So, okay, so you can predict somebody's reading level by the size of their feet if you go across all the grades together, right? Because what would be the confounder? The grades, within first grade, probably having bigger feet doesn't help you read. But if you're, 6th graders can read better and they have bigger feet, right? So there'd be a confounder here. So correlation is not causation. The confounder would be age, grade, right? Confounder would be age here. And what? Do artificial sweeteners cause people to weight gain? Sometimes people who drink a lot of Diet Pop are also people who are heavier. They tend to be heavier. But does that mean that sweeteners are causing the weight gain? Maybe people who want to lose weight are drinking the Diet Pop. Maybe it's the weight gain that's causing them to drink Diet Pop. So you don't even know which direction it goes in. So it's so you don't even know there's a confounder here, and you can't, you don't even if it causes it, you don't know. It doesn't tell you which direction the causation goes in. So you could say, you have no idea. You can't even tell the direction of causation. Just from the correlation. Even if there was causation. Because the correlation is going to be the same, right? X versus, if you put X predicting Y and Y predicting X, it's going to be the same correlation. So that doesn't tell you anything really that way. So you have to be careful thinking correlation is causation. All right, now moving on. Let's see. All right, so read this. Read these summaries. They're really important. And they're good. Okay, so you can read that on your own. And let's move to the next chapter. It's the standard deviation in the regression line. Okay, so what's this chapter about? Well, so how can we use the correlation coefficient to make predictions, right? To estimate Y for a given X. We know there's a correlation, a high correlation. That means that you can get a better estimate of one variable given the other. And how are we going to do that? Well, there's basically 2 ways to do it. The first way is by understanding really what R is. Remember, R is measured in terms of z-scores. So if basically this way tells, if there's a perfect correlation, R is equal to 1 or negative 1, and we can perfectly predict Y from X. Okay? So what does that mean? It means that if you go up 1 standard deviation from average in the X direction, then Y will go up 1 standard deviation from average in the Y direction, right? And all the points will lie on the SD line. And the same if it, you could also have a perfect negative correlation. If Y went up 1 standard deviation from average, then if X did, then Y would go down 1. And all points would be, basically you'd have your ZY equals ZX. You'd have the same z-score in both if it's a perfect correlation, right? So for example, if we had a perfect correlation between height and weight, if you were 1 standard deviation above average in height, then you'd be 1 standard deviation above average in weight. And all you'd have to do, I wouldn't even have to look at you. You could tell me what your height was, and I'd know what your weight was. Obviously, we don't have that. So what if R is very strong, but not 1? What does that mean? That means that if X increases 1 standard deviation, then Y only increases not a whole standard deviation, but 0.8 times. That's the fraction of the standard deviation that it would increase on the average. I'm saying on the average because as soon as it's not perfect, it's not true for all people. If there's going to be scatter, this is going to be on the average. Same with negative 0.3. If X increases 1 standard deviation, then Y decreases only 0.3. The negative means that an increase would be associated with a decrease in the other variable. And what if R is equal to 0? That means that if X goes up by 1 standard deviation, then Y increases or decreases by 0 on the average. It tells, knowing X doesn't tell you anything about Y. Okay? So that's how we use R to make estimates. So what that is saying, in effect, is that the slope of if this is the slope of the standard deviation line, right here, when R is equal to 1, rise over run. If you go over 1 standard deviation in the X direction, then you go up 1 in the Y. That's the slope. If you went over 2, then you go 2, etc. It's just SDY over SDX. And then that's the slope of the SD line. Okay? And then the slope of the regression line is not that. It's if you go over 1 standard, this is again rise over run, and if you went 1 standard deviation in the X direction, you wouldn't go a full standard deviation in the Y. You'd only go a fraction of that, and that fraction is R. So this is it. This is the slope of the regression line. And you're going to be using this a lot, so let's star it and remember it. And you're definitely going to have to remember this on the next exam. So just make sure you know that. R, and it's going to be very intuitive, okay? So what does this mean? Remember, R is between 1 and negative 1. So unless they're the same, when R is equal to 1, they're the same. So the regression line is always less steep than the standard deviation line. It's always flatter by a factor of R, okay? It's always a flatter, more horizontal. It's closer to 0. You don't have a perfect correlation anymore. So it's some mixture between when R is equal to 0, like right here, you've got a regression line that looks like that in scatter. This is R is equal to 0. And when R is equal to 1, you got this perfect correlation, right? Like this, R is equal to 1. And anywhere between that, this is R equals 0. And anywhere between that's going to be flatter. So for example, this would be R equals 0.5 because it's halfway up. This R equals half as steep. So it's in relation. R is in relation to the standard deviation line. If R was 0.8, it would be way up here, etc. If you tick this off, this was 0 and that's 1, and ticked it off, here's 0.5, here's 0.8, etc. Okay, so that's the idea. And so here I say the regression line estimates the average of y for each value of x. Okay, let's go back to our, what's this data on? Height and weight. All right, so let's look at data on height and weight so we'll understand this better. So let's go to our computer and let's look at a different set. So we'll go here and let's not choose the states. Let's just choose, I'm just going to choose a really simple data set. There's less people in the summer, so I'm just going to look at our summer survey and look at the scatter plots and pick height on the independent. Do we have height here? I hope we do. Shoot, did I? Yeah, it's up here. Here's height. And then let's height as a predictor of weight. All right. So we've got this correlation of about 0.678. And how do we get this regression line? Here is the regression line, and here's the standard deviation line. And you can see that it's more steep. The red one's the standard deviation. And this 0.7 is, you know, it's about 70% as steep as this one. Okay? But how do we get this regression line? We know how we get the SD line. That's the line of equal standard deviations away from the average. The average is right here. So if you went over one standard deviation in the x direction and up a full one, you'd get on this SD line. And if you went over 2 and up 2, etc. All right, but let's get rid of this and this and see how to get this. So let's look at something called this regressigram. Okay, so what is this? I can make as many bins as I want here. And what it is if you divide this height up into vertical strips, like here's all the people who are, whatever this is, maybe 78 inches, there's only one person. So this horizontal line is the average in that vertical strip. Like here, there's a few people, and this is the average right here within this vertical strip. Okay? So all these little, they're spread. So the people who are 70 inches, there's a lot of them right here. And here is the average. So what the regression line tries to do is the best fit between all those averages. It's trying for each height, like the people who are 70 inches, well, some of them are really light. 70 inches is 5'10", and some of them only weigh like 130, but some of them weigh 250. So what this little horizontal line here, which looks like it's about 175, that line estimates the average for all the people in that strip. And of course, we can't fit a line through every little average, but it's the best fitting line. Like this one's way off. Because this person is is way up here. It's one part we can't fit that. If we tried to fit that, we'd miss a whole lot of other ones. So that's what the idea is for what a regression line is. Okay? Which is different than the standard deviation line, which, look what it does. It overestimates here and underestimates there. It has to do this because this line right here, the regression line, is a line between a perfect correlation and zero correlation. Zero correlation, which would be flat here. It's taking into account uncertainty. All right, so let's go to the, back to our PC. Our document camera. Any questions so far? Okay, so let's look at this. What does it say? When are they the same, the SD? They're the same when R is equal to plus or minus 1. Because the slope of the SD line is, this can't be, is plus or minus this, and this is, this is, so they're the same when R is equal to 1 or negative 1. All right, and here, I just described this. The horizontal lines represent the average weight for girls. The regression line is a line that fits best through that. Okay? That's what this regression line is. I think you understand that pretty well now. Do you? It seems like you do. All right, so now, how do we do these regression estimates? Well, we're going to learn it. This first method, this is a regression method, we're going to learn by converting to z-scores. And then we're going to learn another method by using the regression equation this hour. So this one is by converting to z, then multiplying by r, and then changing to a value. We'll call it the three-step process. We convert, okay, so we get zx times r is going to give us zy, and then we're going to give a value here. All right, so let's look at this data. Much easier to just go through it. So here's a data set. All we need is the average and the SD and this correlation coefficient, and we can make regression estimates. Remember, they're based on z-scores, because we want to, how else are we going to compare inches and pounds? We can't, so we have to have the standardized measuring stick, which are z-scores. So you always convert. So here's zx, and this is zy. We want to get from zx to zy, and we're going to multiply by r to do that. Okay, so let's look at this. 71 inches. So what is, somebody who's 71 inches is, what's the z-score? So z is value minus average over standard deviation. So 71 is the value minus the average, I'm looking right here, over the standard deviation. This is all inches, and the inches cross out, we just get a pure number. That's 2. So this person is 2 standard deviations above average. All right? So they'd be, where would they be here? Here's the average, just to get a visual. Whoops, there's the point of averages down here. And so we're talking about somebody who's, what, 71, right here. And so now there's 2 estimates. One is the regression estimate, and that would be the SD. Okay? Now, if there are 2 standard deviations, you went over 2 standard deviations in the x direction. So go over 2 standard deviations. And if we went up all the way to 2 standard deviations in the y direction, we'd get on the SD line. But we don't. We only go up a half of 1. We only go up 1 standard deviation in the y direction. That's what we're doing. 1 standard deviation. That's why we're multiplying by r. Okay? If we went up a full 2, we'd get a z-score of 2 here. And then when we'd get 2 of these, 20, 50, above 1, we'd go all the way up to 185. If this person right here, this person, 185, is on the SD line, because they're 71 and 185. They're 2, 2 in z-scores. This person right here is just as heavy as she is tall. Okay? But most people aren't. Most people are below that. And so our regression estimate isn't that. It's what? It's this is our regression estimate. And our regression estimate is what? That person is 71 inches and only goes up 2 times 0.5 has a z-score of 1. So that's going to mean what? She's only going to be 25 pounds above average. Excuse me. 25 pounds above average. Her z-score is 1. So you start at the average to get the value here, and add one of these, 25, and she's 160. She's just one above. You know, I'm just using this formula. Z equals value minus average over standard deviation, and then it's the same thing as what? Now we get a value equals average plus Z times the standard deviation. That's the same thing. That's all I'm doing here. Okay, so now, so she's 71, 160. So here we go, and we can see across here, she's 160. So most people, it's sort of regression towards the mean. Here's the mean, and we're kind of uncertain. We only have R equals 0.5. So it's a mixture of a perfect and zero. If there's no correlation, I just guess the average. So this is in z-scores. Z. This is in z-scores. That's supposed to be z-score. And in z-scores, what would she be? 2 and 1. That's her z-scores. So that's the idea. We can do the rest of them. Okay. So let's do the rest of them. Somebody who's 65, that's right at the average. So their z-score is going to be 0. 65 minus 65 over 3, that's 0. So you multiply by R and it's still 0. And so what is it? Just 135 plus 0. So it's just 135. And the point of averages is on both lines. So that's the point of averages. Let's write it down. So that's the point of averages where the two lines cross. And it's a z-score of 0, 0. In this case, it's what? 65 inches and 135 pounds. These are for girls. 5'5" and 135 pounds is the average. And that's a z, in z-scores, it's 0, 0 in z. Okay? And the next one is what? What's this one? This is one standard deviation below average, right? It's 62 minus 65 over 3. So that's -1. Now, then times 0.5. That's -0.5. So we'll say 135 plus -0.5 times 25. So we're going to be subtracting off 12.5. So we get 122.5. And that's this gal right here. She's 62 inches. So she's here. Her Z, you see, if she was on the SD line, so here she is at 122.5, but her, if she was on the SD line, she'd be -1. So she'd be at 110, 135 minus, so she'd be down here at 110. So let me, how can I say this? Like, all right, so here's your SD line. And here's the flatter regression line. And do you see how for people who are above average, the regression line is, our regression estimate is less? And here, our estimate is more for people below average. Basically because there's some mixture. Look, when you're making a guess, you're going to mix together the average, which is right across here, at 135 right here. You're going to make a mixture between a perfect correlation and nothing, right? It's going to be a mixture between those two. And so when you're down lower, you're actually, the best estimate is to estimate closer to the average. When you're up here, you're still doing closer to the average, but it's lower. That's the idea. All right, I think that's enough. I think such a thing as over-explaining. I might have just done that. I hope not. Let's move on. Yeah, question? It's just because because the graph is so messy here, why don't we look, do you want me to go over this one or online? This one? Okay, we can just do it online. It's just kind of messy. I'll just do it online. I don't have the same data, but maybe it will help. We can just take a quick look. So let's get rid of this regressigram. Let's start over. All right, so what are we doing here? We're going to look at the relationship between these two lines, the regression line and the SD line. All right, this is the point of averages. Where's our data? Here's our stats. So this is right here where they meet is the point of averages. So for height, it's about 67. For weight, it's about 160. Now, let's just see. What are the standard deviations here? So if we went over however many standard deviations, let's say really doesn't matter, and go up the same exact, we're going to get on this, the same exact in weight, we're going to get on this red line. Does that make sense? So if you're exactly the same in height and weight, you'll be on this line in terms of z-scores. But most people aren't, right? That's called regression to the mean. So this is a better estimate. This is a better estimate. And if you went over however many, I'll just draw a right triangle anywhere, however many, once you convert it to a z-score, that tells you how many standard deviations you are above or below average. Like when you're right here, your z-score is 0. So so if we multiply by our correlation of 0.67, we'll just get 0, right? But let's say whatever you are up here, let's say you're above, and then we multiply by 0.67. You see, we don't get all the way up. If we took exactly the same z-score, you get all the way up, but you just multiply it by, we're about 2/3 of the way up. Does that make sense now? Now let's go in the other direction. Let's say you're going negative z-score. So however far you are below average in height, if we went exactly that z-score down, we'd get all the way down to the red line, but we don't. We take it 2/3 of the way down, and that's our regression line. Does that help? Good. Somehow it's just easier to just see it simpler rather with no calculations, just the idea of it. That is the idea. So what are we doing next? Let's see. Now we're going to do the regression line. Okay. So now just taking a peek at this data right here, what we're going to do is get the equation for this regression line, which is right here. It says weight is equal to some intercept plus some slope times the height. That's the equation for this line. So what does that mean? That if you were 0 height, you'd weigh negative 234 pounds. So it doesn't make sense outside the range of where the values really are. But it's another way to get regression estimates. Just plug in a height, and the equation will give you the regression estimate. So if you plug in 70 here, it's going to give you that value right there. Okay? Does that make sense? So let's do that. And let's go to the dock camera. All right. Now, so the regression line. So we've been making these estimates by converting to standard z-scores, multiplying by r, etc. Another method is just getting the equation for the regression line. So here's an equation for any line. You probably see it. This is in statistics. We put the intercept first. So you usually see y equals mx plus b. Why we're doing it is we're going to have a lot more variables. We're going to add on a multiple regression. And so these are these parameters we're estimating. So we call it, the intercept is called B0 or beta 0 that we're estimating. Then our first x variable, like if you have, this is x1, is B1, or this is our Roman letter, we're going to be estimating a beta 1. Then we're going to add an x2. So we'll do B2 will be our statistic to estimate a beta 2 for x2, da, 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 da. So that's why it's in this form here. It might not be used to. You usually see mx plus b. But here, so this right here is the intercept, the y-intercept, and this right here is the slope. All right, so the equation we just need to get both of those. And we know the slope already. We know this slope, all right? So we can get that. Let's just move on down to here. All right. I decided to do some real data here. I don't know if that's helpful or not, but I looked up our data. Just for the females here, I decided to do. And so there was 158 female students here. And you can look it up on, it's on our data program. And they reported how many drinks, this was on survey 2, and how many hours they partied. This is not true. The scatter plot was not roughly football shaped. It wasn't. We can look at it later, but let's just assume it is for now, okay? All right, so now, what are we going to be doing? All right, so here, first let me tell you what I got. So 2.6 hours of parting was the average, with a standard deviation of 4.5. This is kind of rounded, but they're accurate. And then drinks was 2.9 drinks per week, with that's the average, with a standard deviation of 6.2. And our correlation was about 0.7. That's our correlation. So if we wanted to find this football shape is going to be to do estimates. We can get a regression equation that's completely valid, even if it's not football shape, but this is to do inferential statistics with this, and we're not doing that now, so it doesn't matter. So this doesn't make any difference right now. So we're just finding the regression equation, okay? So let's do it. So for estimating drinking from partying, so do you know which one? If we're estimating drinking from partying, this is going to be on you're estimating y from x. So that's how that's going to be. So this is y and this is x. Whatever you're estimating is y, okay? All right, so we've got that. Now, going along with this equation here, let's just write it here. What do we have? So this is going to be, whoa, whatever you're estimating is y, and look what I just did. Oh, we are estimating drinking from partying. So why did I write this? Y is drinks and x is partying. Sorry about that. Whatever we're estimating drinking, okay? So drinks are going to be estimated from partying. So let's just say, so what do we need? So we're going to get, this will be our intercept plus something times x times drinks. All right, so that's what we're going to do. And so this is B naught and that's B1. All right, so first the slope. So our slope, P1, we're going to get the slope first. That's the slope. Is equal to r times s dy over s dx. So what do we have? We have 0.7 times, okay, y over x is 6.2. Over 4.5. So this is drinks per hour, right? Okay. So I did that, and I got almost 0.96 drinks per hour. So that means on the average, people are having 1 drink per hour being at a party. Does that sound right? When you go to a party, do you have about 1 drink per hour? I don't know. You have more? You go in and you get averaged over the party. You might start off with more, but then by the end, you keep, I don't know. This is the average. Some people don't drink at all, so that's what we're doing. That's 1 drink per hour. So that's what we've got. So that's what we can put in where? Right here, 0.96. So now how are we going to get this intercept here? Well, the intercept, this equation is going to be true for every single point on the line, right? So what point do we have? What can we plug in for y and x? To get this, we can plug in for x, the only point for x we have, we can plug in the point of averages, And we can do the same for y and plug in. See how I'm mixing things up? Why am I doing this? I shouldn't have done this. This is drinks, and this is party. This is party. So this is 2.6, and this is 2.9, correct? When I do the y and x's, I got confused. Okay, so let's do that then. And then we can just solve for this, all right? So what are we going to do? So we're going to say, okay, plug in the point of averages. That's it. And what do we get? 2.9 equals beta naught plus 0.96 times 2.6. All right? All right, and then when you do that, what did I get? I got that this is equal to 0.4. So there's my equation right there. Okay? Any questions on that? Okay, so just so you don't get confused, we're predicting drinks. This thing right here is drinks, D, and that's party. The longer you're at the party, the more you're drinking. Of course, you know, I don't know. What would be the other thing? If you're predicting how much you party from how much you drink, I guess you're at home drinking and you're saying, getting all wide, saying, now I got to go to a party. I don't know. I think it makes more sense to have party as the x variable. Okay, so now let's say we want to use this to make a prediction for somebody 20 hours per week. Instead of converting to a z-score, now that we have the equation, we can just say, okay, y equals 0.4 plus 0.96 times how much they party, 20. So that's going to be about, so this is 19.6. So that's about 19.6 drinks. So how to interpret the slope? We just said the slope is what? On average, people consume about, on average, people consume, this was at least these girls, consume about one, we can just say 0.96 drinks for each party hour. And what is the intercept? The intercept means what? The intercept means for those who, on average, people who party what? People who party what? 0 hours. The intercept is when you plug in a 0 here. So if you're not partying at all, on average, people who party 0 hours, what, drink about 0.4 drinks per week. These are drinks per week. Okay, that's the idea. We can look at your data if you want. Let's see what time we have. We can check it. Let's see how close we came with that equation. I did a lot of rounded figures here. Okay, these are all rounded, so it's not going to be exactly that. All this is rounded, but let's just look at it. So let's look at our data. This is your data that you answered on survey 2. So let's just check it out. So, stat 200. So this is, okay. So let's go to the scatter plots. And drinks and partying. Do you see them on here? Oh, party hours per week and drinks. Okay, so now we're going to look, we're going to do a split. We're going to split because I just looked at the girls. So I'll split here and split plots. All right, so this is the one I looked at right here. And how come it's not working? How come I didn't? It doesn't look like Did I use a different data set? I must have used a different data set. I'm really sorry. Let's look at what the stats are here. Yeah. Well, no, 2 oh. Yeah, I used a different data set. I'm sorry. So it doesn't work out here. Here's your data set right here. So sorry about that. Okay, so now let's move on and let's go to the next. So here's our summary. This looks good. And let's go to the document camera. And we are almost done here. Anybody have any questions? Anybody have any? Sorry, I didn't use your own data set. I used somebody else's. I'm sorry. And now, let's look at this. All right, so what about these? We make a prediction, but we want to put some wiggle room around it, right? So we have to look at the errors around the regression line. That's all this is about now. So you make a prediction, and now, how are we going to look at these errors? So here's an example. So here's what? Exams and final of a group of students. All right, and so this person did much better than predicted, so there's a residual here. The residual, the prediction error, is what? The actual value minus the predicted. That's what it is. That's the error. So it's this distance from here to there. That's your observed minus your predicted. So this person has a residual that's negative. Observed minus the predicted, and these two will be negative because they're below the line. So you take the observed minus the predicted, and they're below the line. Now, it's kind of hard to read it this way, so a lot of people just look at, instead of plotting the finals here and the exams, they just plot the errors. So they're just going to, the errors, so if somebody's exactly on this line, they'll be right here, perfect prediction. And now you can see better, this looks like 17. So this looks like the residual for point A is about 17. It's just easier to read it here. And if this was -7 and this was -22, then you can see, okay, B, this distance is -22, observed minus predicted, and this one's -7. So it's just easier to read when you look at the residual plots. All right, now for any regression line, the average of all the errors is always 0. So if you added up all these errors, it's 0. So that's not a good measure of the size of the errors. So what do we do instead? We take the standard deviation. So what we do is we take this root mean square, all right, of the deviations. So let's just write it up here so you remember. Okay, so here, right here, our prediction error is what? Our actual value, which is y, minus, we call our prediction, we put a little hat on it for our prediction. So that is our prediction error. Now, what is the standard deviation? What is the actual size of these? Well, I say if you took the average, they average to 0. So that's not a good measure of their size. So instead, we take the standard deviation of them. So let's do that. So the standard deviation of the errors is what? What's the standard deviation of all these errors? Well, how do we take a standard deviation? First, we get the deviation. So this is the deviation, y minus y hat. That's a deviation. It's just an error. But if we added them and took their average, it would be 0. So we square them like we always do. Now we're squaring them. And then take their average, which means summing them all up, that's the summation sign, and then dividing by n. That's the variance of them. But we want the square root of that because we squared them, so now we got to square root them. So that's called, the standard deviation of the errors is also called, what are we doing? We're taking the square root of the mean of the squared errors. That's another word for it. So, skip down to here. That's what it is. Now, instead of doing this, which would take us a very, very long time, if we know the correlation coefficient, we can use this handy handy relationship. This is really cool, this formula. So this is another thing you need to know. All right, so far what do you need to know? The slope, r times sdy over sdx, and this. All right, so how does this make sense? How does this make sense? We're not gonna prove this to you, but just show in the extreme cases. Look, how about when r is equal to 1? Okay, right here, when r is equal to 1. Okay, what happens when r is equal to 1? R is equal to 1. What does the picture look like? I'm going to have a picture. Let's just do it in this first quadrant here. Let's just have a picture like that. So r is equal to 1. So is there any error? Is there any error when r is equal to 1? So the standard deviation, they'll all be the same. There's no errors, so the standard deviation, the average should be 0. And is it? Let's use that formula. When r equals 1, the standard deviation of the errors is equal to what? Plus or minus 1, I should say, plus or minus 1. It's going to be 0. Because if you put a plus or minus 1 in there and square it, you get 1 minus 1 is 0 times anything times 0. So that works out, right? You get 0. How about the other extreme? So that's this one. How about when r is equal to 0? Let's do that over here. So when r is equal to 0, what do we have now? What does that look like? Let's just think about it. It would look like what? R equals 0. That means that knowing x, you just have a cloud here, knowing x tells you nothing about y. So you just have a horizontal line. This is r equals 0. And you have a lot of error. Your error is what? Your error is the typical distance from the average. This is the average y. No matter what x is, our best prediction would be the average y. And our error would be the spread around the y's, which is the standard deviation of y. So when you put a 0 in here, that's exactly what you get. When r is equal to 0, you get the SD errors right here. The SD errors is equal to what? SDY, the typical spread around the y's. So doesn't that make sense? When you stick a 0 in here, you just get 1. So those two cases make sense. This is just the standard deviation, the spread of the y's. It's just the standard deviation of y, the typical standard deviation of the y. All right, so that's the idea. And let's just do an example, and we will be done. All right. So let's do an example. We've got our 5 summary statistics so we can make regression estimates. All right, so we can do this pretty easily. Find the slope of the regression for predicting what? Finals. So finals is y, and this is x. And this is our SD line here. This is our regression. All right, and there's our correlation coefficient. So let's get the slope first. So our slope, is equal to what? R times SDY over SDX. So R is 0.6, and now Y over X, 10.3 over, I'm just looking at these, 9.2. Okay? And that's 0.67. All right, so now we've got this equation right here. We know, I'll just do finals, or y equals what? Some intercept plus 0.67 times your exams. It's easier for me to keep it straight. If I keep it, that's y, right? And x. So now, what are we going to do? We're going to plug in the point of averages. So let's go for it. So this is, for the final, we'll plug in 73.6. And that's going to be equal to beta naught plus 0.67 times 83. Just plugging in the point of averages. So what is beta naught? Beta naught is equal to 73.6 minus 0.67 7 times 83, which is 17.99. And that's what you get put right there, 17.99, and there is our equation. We are done. Okay, so now use this equation to predict the final exam score of a student with a 90. So you're just going to put 90 in for exams. So we'll say the final exam score, the predicted final, we should put a little hat over it, equals 17.99 plus 0.67 times 90. And when I did that, I got a 78.29. So that's got to be this right here. That's what I got, 78.29. That's what that is. All right, so now what? That's for... All right, so do you think the prediction will be exactly correct? No, because look, there's a whole little column of people around 90. There's dots here. So now what's the typical error? What's our wiggle room? No. We have to have, there's got to be some wiggle room. And that, we need to add the wiggle room, margin of error. So what is it? So, what is it? It's the root mean square error. That's the standard deviation of those errors is what? The square root of 1 minus r squared times the standard deviation of y. So it's the square root of 1 minus 0.6 squared times the standard deviation of y, which is 10.3. Now, you notice this is going to always be less than 1, right? Unless you have 0 there, it's going to be less than 1. So your answer is going to have to be less than 10.3. In this case, I got 8.24. So that's the wiggle room. That's the margin of error, okay? And so, not the margin, it's for just, it's one standard deviation. So now attach that wiggle room to the point estimate, okay? To give it a range instead of an exact one. So what do we want to do? We want to take our, instead of just estimating, doing a point estimate, we're going to take our prediction plus or minus 1 root mean square error. So our prediction was 78.29 plus or minus 8.24, and then we're going to get this range. And it's going to be a 68% confidence interval if you have that football-shaped cloud, and we do in this case. So this is going to be between 70.05 is our lower, when you subtract 1 root mean square error, all the way up to 86.53. Okay. Now, suppose the student really, this is their actual, really actually got an 80, actual is equal to 85. And the predicted is what? We predicted them to get 78.29. So now they want to know what the residual is. Well, it's just the actual minus the predicted. So the residual is just another, all this language is just another word for how far off he is from the line. Well, he actually is higher. So it's just the actual minus the predicted, which is 85 minus 78.29. And that is 6.71. So it's about in the range. We say the average error is 8.24. He's a little bit below average error. Pretty close. Okay, so now, last 5 minutes is if you have a football-shaped cloud, you can use, like this is the actual data, and you can use, this is the regression line, and what? You want to take a picture of me? Is that what you said? You're interrupting? Okay. Right here, but this is on the video. So here you can take a picture. So as we were saying, if you have a normally distributed, if you have a football-shaped cloud, the idea is if you have this football-shaped cloud within any vertical strip, I don't know, you can take a vertical strip here, what you've got is a little normal distribution. Okay? You've got a little normal distribution inside here. And So if you go, here's the regression line. If you go up 1 standard deviation, 1 SD, and there's 2 SDs, and minus down 1 SD, and down 2 SDs, you've got these little normal curves inside every vertical strip. It's hard for me to draw it because it's like on an angle, but basically the idea is within every vertical strip, here's centered at 0, and if you go up between this distance from here to here is 68% of the data. And if you go between 2 standard, you have 95% of the data. This is if you have this particular type of cloud, basically. It's bivariate normal. We'll learn about this more, but for now, we have it here, and so we can use our rules of thumb from the normal distribution. So let's just do this last example. So about 68% of the time, our predictions of finals based on exams will be right to within what? This is going to be within 1 root mean square error. So that was 8 point from the previous page. That was our root mean square error, right? So 68% of the points will be within your prediction plus or minus 1. So 68% will be within prediction plus or minus 1 root mean square error. This 1 is the z-score. Z for middle area equals 68%, just like that picture. And 95% will be within 2 times the root mean square errors. So you'll take your prediction, okay, and so this will be within 16.48 because this was 2 times 8.24. And 82% of the time, so what do I mean? So you have your prediction, so I mean the prediction, so 95% will be within the prediction plus or minus 2 times the root mean square error, and our prediction was 78.29, and that's plus or minus 16.48. And our last one will be 82% of the time will be, so we just need to find the z star for the critical value for 82%. So you're going to get what? If I looked it up, it turns out to be 1.35. I'll just show you here. Between 1.35 and negative 1.35 is 82%. So that's what we're going to be using here. Okay? So it's going to be 1.35 times the root mean square error. So that's 1.35 times what? 8.24. And when I did that, I got 11.124. I hate to go to all these decimal places when it's so approximate. It's about 11. I mean, we don't really have that level of precision because all of this is, but that's the idea. And I think we are done. And have a great weekend, and I'll post the, have fun if you're celebrating unofficial, and and be safe. I mean, why get so drunk? It's crazy. But, you know, you're young and foolish sometimes. And I'm old and foolish sometimes, but control yourself. Okay? Have a good weekend.